Problem number 3 is 3258. It is an RLC circuit. The L value is 1.0 times 10 to the minus 6 Henry. We don't know C, we don't know R. They are in series. It is an FM radio. And I tune in on a broadcast. I do that by varying the capacitor. This arrow through the C means that the capacitor can be varied. And I have broadcast station number 1, which broadcasts at an angular frequency of 6.00 times 10 to the 8 radians per second. And I tune dead on to this one. But there is an annoying nearby station which radiates at a frequency almost the same as this one, but I don't want to hear this one. Well, let's first calculate what the value for C is. If I tune exactly in with my variable capacitor on this frequency, then omega 1 must be omega 0, and omega 0 is 1 over the square root of LC, as we have seen many times for a series RLC circuit. And so you'll find that C, I square this, equals L1 divided by L omega 1 squared. I know what omega 1 is, I know what L is, and I found, I could have made a mistake, 2.778 times 10 to the minus 12 farad. So I know how I should tune C in order to receive omega 1 at its resonance frequency. But now we're also told that the mean power that's coming from the second station delivered to the resistor R, which is presumably the loudspeaker. So from station number 1, that is 1/100th of the mean power through a complete cycle of station number 1. And the question now is, what is R? Let us make I'll put this here because I may need this again. Let us remind you of what the maximum current I looks as a function of omega for a given LRC circuit. In the beginning this is more or less linear. It flares up, we call that resonance, and then it dies off. And right here at the maximum value for I0, which is the resonance frequency, omega 0 equals omega 1, because that's the way I have tuned the system. And now my second frequency comes in here, and so you see that the current is highly reduced so to the point that the power is only 1/100th that the resistor receives from station number 1. What is mean power in general? Well, it is the VRMS coming in through the antenna times the IRMS driven in the circuit times the cosine of phi. This is the general equation for power delivered to that resistance R, and you have seen this before. The current that is going to flow in the system equals I cosine omega t minus phi. This is something you have seen before. It is only to refresh your memory. And the way that you can best solve this is in the following way. Your I0, or let me first calculate the value for phi. The value for phi is given as follows. This is R. This is omega L minus 1 over omega C. You know, we got this from phasor diagrams, and we call this the impedance, which is omega L minus 1 over omega C squared plus R squared. And so the tangent of phi equals omega L minus 1 over omega C divided by R, and so the cosine of phi equals R divided by Z, which is this whole square root. And we have assumed now, or I will assume, that the input voltage RMS from both stations is exactly the same. So now, how about the power ratios? The power ratio of 1 over 2 mean values would be I RMS circuit 1 cosine phi 1 divided by I RMS circuit 2, not circuit 2, station 2 times cosine phi 2. Remember, the values for R, L, C are values that are going to be given. In fact, you have to calculate R now. And this value now we want to be 100. Now at resonance, cosine phi 1 equals 1 because phi 1 equals 0. You can immediately see that here. Let's write down what I RMS, I don't know what problems I have with this sheet. Let's write down now what I RMS is in general for an RLC circuit. It is I0 divided by the square root of 2, and that would be V0 divided by the square root of 2 times that value for Z. Let me write that in, omega L minus 1 over omega C squared plus R squared. And you have seen this many times before. So if now I go to station number 1, I get that I RMS for station number 1 equals simply V0 times the square root of 2 times R, because when this is 0 at resonance, I only have an R here. Cosine phi equals 1. If I now go to station number 2, I RMS for station number 2 equals V0, and we have assumed that the V0s are the same, square root of 2, and now I get this square root, which is now omega 2 L minus 1 over omega 2C squared plus R squared. But I also must multiply by the cosine of phi. And the cosine of phi equals R divided by that same square root. So the square root occurs twice. And so now my task is to calculate the ratio P1 divided by P2, which is 100. And so I take the ratios of these two values because the VRMS here is exactly the same as the VRMS here. So when I take the ratio of the power, I can delete the VRMSs and I can also delete the square roots of 2's. And so what do I get? I get upstairs 1 over R, and I get downstairs R over the square root of this, again times the square root of this. And so, maybe I'm going a little bit too far. I could have left you now solving this equation, but I do get, we have plenty of time, so why not? Omega 2L minus omega 2C squared plus R squared divided by R squared. That is now the requirement for that power ratio to be 100. Now C was 2.778 times 10 to the minus 12. L was 10 to the minus 6. And so that gives me omega 2L equals 599.0 ohm. And it gives me 1 over omega 2C equals 601.0 ohm. So this here is 2. So 2 squared is 4. So I get 4 plus R squared divided by R squared equals 100. And when I solve that equation, I found that R is approximately 0.201 ohms. So, with this resistor, you will get 100 times less power from station number 2 that you get from station number 1, and you have exactly tuned your radio, or television station for that matter, on station number 1. But of televisions, the frequencies will be different, I imagine.